You've seen it a dozen times. An astronaut's tether snaps, they drift into the void, and within seconds turn into a block of solid ice. But the biological reality of a vacuum is much more gruesome. Without atmospheric pressure, the liquids in your body, from your saliva to your blood, begin to boil away into gas, while unfiltered solar radiation simultaneously scorches any exposed skin. The void subjects matter to simultaneous, brutal contradictions, tearing, burning, and freezing the body all at once. This happens despite the fact that the universe is essentially an ocean of energy. Our sun alone is a thermonuclear furnace, radiating 384 septillion watts every single second. Zoom out, and the observable universe contains 2 trillion galaxies, each packed with hundreds of billions of blazing stars. With the cosmos lit by more massive furnaces than there are grains of sand on Earth, why is the space between them near absolute zero? To find the answer, we have to throw away our earthly intuition of how heat actually moves. In physics, temperature measures how fast particles move. Hot objects have particles jiggling furiously. Cold objects slow down toward absolute zero. Earth's air holds 25 quintillion molecules per cubic meter. Deep space, however, is a near-perfect vacuum, with roughly 1 atom per cubic meter. Without particles to collide, vibrate, or carry energy, heat, as we understand it, cannot exist. You cannot measure the temperature of nothing. Because temperature requires matter to manifest, the vacuum of space has no inherent temperature at all. It is simply empty. This emptiness eliminates the 2 primary ways heat moves on Earth. There are no solid surfaces for heat to travel through by touch, conduction, and no air or water to carry warmth through currents, conduction. That leaves only radiation. Stars emit energy as electromagnetic waves that cross the void without heating the vacuum itself. This energy only creates warmth when it physically strikes a piece of matter. This means in space, heat is strictly line of sight. If you are not directly hit by a wave of radiation, you are receiving zero energy. On the moon, this creates a brutal divide. An astronaut standing in direct sunlight experiences boiling highs of 250 degrees Fahrenheit. But the ground in their own shadow, shielded from that radiation, sits at a constant -290. In the void, there is no ambient room temperature. You are either a direct target for a cosmic furnace, or you are stranded in the dark with no bridge between the two. This binary environment is the central challenge of spaceflight. Every 90 minutes, the International Space Station orbits in and out of the Earth's shadow, swinging its external structures through a 500-degree temperature range. The Parker Solar Probe was built to test the very limits of this divide, flying directly into the sun's outer atmosphere. The probe's heat shield takes the full hit of solar radiation, reaching 2,500 degrees Fahrenheit. But because radiation only heats what it strikes, the instruments sitting in the shield's shadow remain at -238 degrees. This environment makes cooling a spacecraft incredibly difficult. Without air to carry heat away, the vacuum acts as a massive insulator, a cosmic thermos that traps the heat produced by onboard electronics indefinitely. If an object drifts into the deep voids between galaxies, shielded from all starlight, its temperature eventually sinks to a final, universal floor. This baseline is set by the cosmic microwave background, the relic radiation left over from the birth of the universe. In 1964, astronomers using this horn-shaped antenna discovered a persistent microwave noise coming from every direction in the sky. They had found the afterglow of a time 13.8 billion years ago when the entire universe was an extremely hot, dense plasma. As the universe expanded, that initial energy was stretched and thinned, cooling into the pervasive background radiation we see today. It ensures that no matter how empty a region of space is, it still contains enough energy to stay 2.7 degrees above absolute zero. This thermal floor used to be much higher. By measuring the shadows cast by ancient water vapor clouds, like this one, seen as it was 880 million years after the Big Bang, scientists proved that the early cosmos was once 7 times hotter than it is today. As space continues to expand, it stretches this ancient radiation even further. Every second, the universe grows larger and thinner, pushing the background temperature closer to an eternal deep freeze. Against this reality of radiation-dominated voids and billion-year cooling, our environment is a glaring exception. Earth is wrapped in a dense atmospheric blanket. Our air molecules intercept solar radiation, then physically collide and circulate to distribute that heat evenly through convection. The stable, ambient warmth we experience daily exists only within these thin margins, a rare departure from the binary extremes that define the rest of the cosmos. When you look at the night sky, the marvel isn't that space remains a frozen void despite the trillions of stars. The marvel is that we found a way to stay warm inside of it.